name is Ricardo Valls. I'm the founder and president of Valls Consultant, and I'm also a professional geoscientist registered in the province of Ontario with over 36 years of international experience. Today, I'm going to start a new mini-series in these Golden Rockets webinars. We are going to be talking about unusual sampling and exploration techniques. I really hope you will enjoy it. Hello, my friends. I'm here at Wat Griffith Makuat with my good friend Nick, and operating the camera is my other good friend Ricardo Franco, who we thank him for helping us with this little video. I'm going to be talking about Nick's favorite toy, this little drone. You won't believe it, but this is a drone that weighs 250 grams. And I was telling Nick that at the beginning, I never liked drones. For me, it's just a toy, especially the big ones. But once I saw what this little guy can do, I was converted. This is something that you can put in your pack sack, okay? And you are in the field and you look to the mountain, you see a very nice outcrop, but there is a river in between. Do you get wet or not? So you just take your little drone, you fly it there, you look at the rock, and then you decide, okay, this is an outcrop that is worth getting wet with. The other thing, as I will be showing later, is that we can join our iPhone with the many applications, geophysical applications like the Teslameter, and obtain an incredible geophysical map of an area. So I want to pass the microphone to Nick. And please explain us a little bit more about the drone, how it works. Etc.
Thank you, Ricardo. This is the DJI Mavic Mini, the latest model. It's a very small. Its weight 249 grams, which is 1 gram less than the requirements for the license. That means you don't need any license for North America. This is the size if you want to see how big is the drone, basically. This is in centimeters. And you can see how big is in this size, like from the top. It's a very small, you can fit in your pocket. This is the remote control, also very small. And you need the phone, which is attaching to the remote control to basically control the drone. How it works, it's very simple. Just open those things. You're taking the cover for the gimbal. This small guy can fly in the sport mode with 13 meters per second or approximately 40 kilometers per hour. Elevation can go maximum, I think, is around 500 meters, half a kilometer. Let me show you how this is working like that. This is the remote control sticks, just open. You open this way, you attach your cell phone.
That's the part that I like the most because you don't need an extra screen. You're using your cell phone to fly it.
After that, you just turn off this guy, like that. Turn off the remote and start the application. It's a DJI application connecting the remote control to the drone. And now we are ready to fly. It's a real time showing you what is visible on the camera on the drone. Very simple. Just put this stuff up, and the drone is going up. And basically, the good thing is this drone have sensors and GPS, real-time GPS. That means you know exactly where you are. by the coordinates, and you have a sensor showing you how many meters is above the surface on the screen, and you can see everything which is drone seeing. You can put the video, the camera down if you want to do a photogrammetric picture. Basically, we are trying to use this drone, which is the price is approximately 400 US dollars or 600 Canadian. We are in Canada for professional work, or remote sensing for geology and geophysical and geomatics purposes. It's very easy. Just up, down, go front. Now I can rotate the drone like twice, and what we can do, I'm gonna put the video camera, and we can have a video coverage. There you go. We're three of us.
Test number one.
That's number one.
Can you move it? I will call that a success. Test number four, measuring the Teslameter. So, as I explained last time, once we finish doing the survey, we can email ourselves the result of the Teslametry as an Excel file, as a CSV file. This is the raw data, how we receive it. And here I just clean it up a little bit. I just left the XY, that would be the UTM East, UTM North, and the actual value of the Teslametry, the macro Teslas. And here you can see, even in a short fly, as this demonstration, that we have a very nice variability of the data. Now, how does that looks in a map? For that, I use Surfer. And first of all, this is a graphic with the disposition of all the points, there are about 1,400 and something points that the machine measured during the short flight. I did a variogram for all the data and adjusted the line using the power method, and it gives us an anisotropy of 2 and an angle of about 167 degrees. Then using this, I did the grading using the natural neighbor method, and look at the amazing map that we can get. Another interesting application that we have, the GPS Motion X GPS application that records our tracks, and you can then export the data to Google Earth or as an ASCII file that you can use in detail. Well, one of the things that you can do is, while the phone is measuring the Teslas, you can also have GPS working to determine the track and the elevation. I'm going to show you. So you go to your GPS, and I have here, I'm going to show you a track from a fly in Mozambique. That is the record. And if I click on view details, you can see down here the elevations of the track. So you can share that information by email. You select all the emails that you want, and you set that information to yourself. And then you can plot it, as I said, you can plot it directly on Google Earth, or you can extract the elevation values and do your own digital elevation maps. My friend Nick Pascaliev is studying the possibility of extracting the same information directly from the drone. If he's successful, I will probably add a note to this video. Second video, I will be explaining also this option. So, as you can see, you can run several applications at the same time. In this case, Motion X GPS and the Tesla. And today we will be discussing a hybrid of sampling method. And we would be talking about biochemistry. As you probably know, we can group biochemical sampling or biochemical anomalies in 3 groups, like alluvials that get transported very much, alluvials and diluvials that are moderately sampled, like soil sampling, and in situ anomalies like lithobiochemistry, when you sample the rock. The applications and the usefulness of each of these anomalies is clear. When you're doing regional exploration, you will go with the stream sediment and heavy mineral concentrates by sampling the banks of the river, also hydrobiochemistry or biobiochemistry. These are methods that cover large area with a relatively rare grid of sampling. For example, if you're doing a survey of 1 to 50,000, you will get about 4 to 6 stream sediment sitters and no more than 2 heavy mineral concentrates per square kilometer. That would be enough for a scale of 1 to 50,000. Now, and heavy mineral concentrates, they are both taken from the active sediment from a stream. Although you can actually take heavy mineral concentrate from any place in any any rock, any place. This includes paleoplacers, this includes just soil. This includes, for example, crushing a rock down to a powder and doing a panning, heavy mineral concentrate. So heavy mineral concentrate is more ubiquitous. Now, heavy mineral concentrates allows you to an initial volume of material down to several grams, thus enriching the sample sometimes 500 times, 1,000 times. When you're doing this, you're increasing the possibility of detecting anomalies of elements that are not that abundant, like diamonds, etc. So the heavy mineral concentrate, you start by taking a constant. It could be constant. And also it's very important that you take the sample from a site that Mother Nature have accumulated the heavy fractions. And in rivers, this is very simple to determine. It's only a function of the speed of the water. And what you're looking at is places where the stream was going fast and then there was a curve, a meander, or an obstacle in the river, and the velocity of the water reduced suddenly, thus the heavy fraction falls. So you get the sample from before the obstruction. Or, the river makes several meanders. From one part, it excavate, and the other part, it deposit. Well, you take the sample from the deposit part. But the most important, the sample must be representative from the site. Then the process it takes several steps. You need to weigh the sample, you need to sieve it, you need to describe the macro fraction, and then at the end, you start panning. Now, the actual panning, I know really good. They will pan a 10-liter material down to, the 3-5 grams of black concentrate in 5 minutes or 3 minutes. I have seen panners that are able to pan using not a panner, but just a dish or a shovel. So there are people that are really, really extremely good at panning. But even those people that are the exception would require time to process the concentrate. And that is the reason why I believe heavy mineral concentrate is not a common method applied for exploration. It's much faster to get to the stream, put your hand in a plastic bag, grab a handful of material from the first terrestrial river, and you have your stream sample. And that is sent to the lab dries it, and does spectral analysis or a fire assays, and you get your result. In the case of the heavy mineral concentrate, once you finish doing your panning, you can separate different fractions. Like you can separate the magnetic fraction, the electromagnetic fraction, and each of these 4 fractions can be studied under the microscope and sent to the lab for assay. So you get 4 samples per site. Again, as you can see, I'm a big fan of the heavy mineral concentrate, but the problem remains. It takes too much time. Well, I think I found a solution for this.
Usually, more than 90% of that material is just waste. I mean, it doesn't contain any information. So any technique that we can use to concentrate the heavy minerals, which are usually the ones that carry the mineralization, will help us get better results. We are enriching the sample on purpose, which is what we need to get good results from the lab. So normally people do the panning. And for the pan, by the way, I didn't explain the first time. If you're going to do panning normally, instead of the little cup, you have a bucket of 10 liters. And the rest is the same. So, but it is important to always have the same weight. sorry, the same volume. Okay, so 10 liters, you're doing a normal pan, something like this, that you later find out how many cubic centimeters are here. So, and you need a balance. So you fill the material, you weight it, you got volume by weight, gives you the density of the rock. And even that may tell you immediately if there is something good or not, because the more dense the sample, the most important it is. Actually, there is another thing that I forgot to explain, so it's good that the camera turned on. Okay, where do you get the sample in the river? This is a mechanical anomaly, so you need to apply a little bit of physics. You need to sample in places where the water in the stream accelerates, but not too much, accelerates enough to wash the light fraction, or stops enough so the heavy fraction will fall. So good places, an obstruction in the river, like a falling tree, that is usually one of the best places. You pick it up before the water. I mean, the trunk is here, the water goes here, you get it from here. Okay, so that is one of the best. The second thing to know is that the river always do meanders, and from one side he erodes. There, for example, it's eroding there, and then it deposits on the opposite side. So you take the sample from here. This is a good sample. Within the area, try to find out where you see rocks like this. Okay. And I know this is a problem because all these rocks need to be thrown away, but here, in this piece here, is your best concentrate of heavy minerals in the whole size here. So you see, there, wherever you see rocks, that is where you're going to take the sample. You see over here, there is nothing. Okay, so those are the important things. So, okay, let's go back. So as I mentioned, we're gonna, this you do it in the field, but because we have this sample taken before, we will fill this up. You hit it like that, so it will, okay. So, that is your sample. So the next thing, you weigh this, and you know how much it weighs. Then you usually take something a little bit bigger, longer at least. This is too square. So you take a sieve of number 4, which is about ½ an inch. Okay, so you can throw away all the big rocks. So there is the sieve, okay, the invisible sieve. And then we need to make sure that we're going to take a couple of spoons, that this sample is representative of the meter you sample in the wall. So we need to homogenize this extremely well and then do quarters. So this I really discovered like a couple of months ago. A very easy way to do the homogenization is just grab this thing and then you put it up. You need to put it up. You need to put it up. No, sorry. Go down. You need to do that so it will move. Okay. Okay. Now we do the same, but on this side. Be hard. It must rotate. It cannot slide. It needs to rotate. Okay. So you need to do like this. No, it's a brisk movement. Like that, okay? Brisk movement. Brisk movement. Ah, you got it. You got it. Okay, perfect. So now that it's well homogenized, we just distribute it. Make a quarter. By the way, I'm doing something really bad. Okay. And you just throw away 2 parts. And this is your sample. Okay, so we're going to take the sample from here. So, for that, we take a condom. Actually, this is the box. Power play. This is the one that you're going to need. because all the other one has some forms, strange forms and smells and stuff like that. We don't need that. So you just fill the condom with water from the river. Come on. And as I said before, the best one if it doesn't have any oil on it. But if not, we work with what we have. So now that we have the condom with about half the weight water, we just add the fullness of material. I will let you do completely the full one from the side for yourself. Now remember, the tip, grab the tip.
I can't use this spoon anymore, my pockets.
You can put more. Actually, it's amazing. It takes enough material. So, if you see, there is no sorting there. They're just like they fall. So, we grab the condom here, and when I'm gonna do this first movement, and then I'm gonna lift the tip. And we're gonna do a vertical movement. Practice safe geology. So 10 seconds, 15 seconds, really, you don't need too much. And when you finish, you will see that all the heavy fraction are concentrated right here. And all this is like material, clay, etc. So basically by 50% minimum, you have concentrated the sample with the thing that you need. Now, to get the sample, you just grab it from where you want to get. Sometimes you are interested in the really, really heavy ones, you just grab this, the little pit, okay? If not, but at this exploration now, grab all the whole thing, throw it away, and that is yours. Finish.
Okay, so what we did, we pour some material here. Usually the material that you put here is the material that has been sealed. This is just an experiment. So once you put it, see that I have the tip pressed, okay? Then you just close this thing, okay? And you release the tip, and you start doing this movement, okay? 5 seconds, no more. Now come closer and you will see your pan already done. Come here. As you can see, the heavy fraction is down here, the light fraction is here, and the clay is up there.
Oh, yes.
So what you do, it depends. If you are only interested in the heavy, you just grab this bit here and throw away the rest.
Okay.
Usually I would recommend to take more, to take like this bit here. So what you do, just drop it, and this is your sample.
Come on, so easy. Fast.
Yeah, that's your sample.
And ease.
Now, this thing goes into an envelope that I will show you now how you do it. And when it is dry, you can separate the magnetic fraction using a magnet. You can even do that partially here in the condom. You can just pass the magnet and put the magnetic fraction on the top and then throw it away. But it's easier to wait when it's dry and you do the separation. So that, my friend, is your pan sample. You put it, a number or whatever, and that's it. Stop recording.
We're going to explain the use of a condom to obtain a heavy mineral concentrate right in the field if we want to do it. First, we take a condom that has no oil, must be important. Then we pour in the material. In this case, it was a material taken from a creek, a dry creek. It's composed of, all the fractions. So we previously filled the condom with water, then we add the material using a spoon. Of course, this can be done directly in the field. Once we have enough material, we just close it here and start shaking the condom. You can do a little bit of manual mixing, and in just a few seconds we will have a perfect separation of all the fines and all the heavy grains. We throw away this part, the fine fraction. We just select this thing here and pour it, and then this is the material that we're going to send to the lab, that we put on a paper, and we could send the condom to them. It's plastic, so it's nothing. It will not alter the rock in any way, the assay in any way. The reason why it should not have oil is because if it had oil, it will stick to the condom. So this way we have a heavy concentrate, very simple to do. If we dry this and use a magnetic separator, we could also have a magnetic fraction separator. It's okay. That's it. Okay, now that we have the sample that we concentrated in the field, I want to show you some of the preparations that you can do at the office to study your material. So I will show you how to do a magnetic separation and a sort of a heavy or gravity separation, not using any liquids. So let's assume this is a sample, and you are going to need something like this binder. Black color is better because if you have gold, it will look much better here. So let's say that it's a sample. Put it as close as possible to this side of the binder, the top side. So you can find, it is called a gold separator, which is an improper name because gold is not magnetic, but this is a magnetic separator. Put your magnet on top of the material, and then you pull this up, and the magnet goes up and the material will fall. I will show you. So you see how it got the magnetic fraction there. See it in detail. And now I just put it here. That's it. Now, if you don't have one of these, there is a simple method of doing. One second. As I would say, if you don't have a magnetic separator, just find a normal magnet, like a fridge magnet, and a piece of paper. And you put the magnet inside the piece of paper, and again, you see, you pick up the magnetic fraction. Okay, and then you just take the magnet out, and the material falls. So I'm going to finish taking the rest of the magnetic fraction. And if we sampled when we were doing the panning, we went down to
the black material, the black sand, this here was composed mostly of heavy fraction and the magnetic fraction and the electromagnetic fraction. So we separated the magnetic fraction. Now, the equipment that we're going to need to separate the heavy fraction, not using any liquid, is a simple straw. You take a straw, and for a little time, you take a pin and you press the end of the straw. So when you're gonna be blowing, okay? So the air will go out like a stream. This way, you're gonna blow the material, and because the gold is much heavier than the rest of the sample, the gold will remain in the binder. And because the binder is black, it will be very easy to spot. So you just need to learn, this how strong you need to blow. But with time, you get practice to it. So we start. So you see there, that is a little grain of gold. So this is how you can use your straw to separate the gold grains, or in general to blow away the light fraction. Now, the next step is, well, you can study this with a magnified lens, of course, but I will strongly recommend you to acquire a Dinolite microscope. Dinolite microscope, this little thing here, gets connected to the computer, and I will go and show you now how it looks like. And you get, well, in this model, you get even polarized light. You get a augmentation up to 250 times. You can use this Dinolite microscope to study polished section, thin sections. You can take it into the field to observe the aphanitic mass of a porphyry rock, etc. When I bought this model, it was about 200 Canadian dollars. Now it's about 400, 480. But anyway, it is much less than a normal microscope or binocular that will cost you in the thousands of dollars. To buy this thing, you can go to Dinolite, Dinolite, or as anything that you will need in geology, you can go to Deakin, Deakin. It's a geological store here in Vancouver, and they offer absolutely everything from hammers to microscopes. So now let me show you how this microscope works in the computer. So this is DinoCapture, the software that allows you to link your Dinolite to the computer or a laptop, or I believe that there will be soon a connection to your iPhone or your smartphone. So that will make Dinolite completely portable. As I mentioned, you can increase the size of the things up to 250 times. And the software allows you to do multiple things like measuring the size of a grain, taking photos. Okay, so you take a photo, click on this, and you get a photo. You can take a video too, a VGA or a time-lapse video. I will not take a video this time. You can measure the size of a grain. So that one would be 0.7 millimeters. You can do annotations. And all these pictures can be then downloaded to your computer. and you just move your sample around. Look at that piece of galena there. You see the shiny. So this microscope, portable microscope, will be a very useful tool for you in the field and in the office.
My name is Sergio Troncoso, and I work here at ACLABS in the mineralogical department. And I'm here just to show you some of our capabilities that we offer at ACLABS. Here we have a MLA quant scan, quantum fig, and you can see that we offer with this machine various types of mineralogical work. We can determine bulk mineralogy, mineral identification, quantification, liberation, association, mineral association, and so forth. This will be very beneficial for your getting to know your ore or for processing procedures for your plant. We have here our. This is what we mount the samples. These are polish sections. We can mount also thin sections that we can map and determine very similar or better than actually doing a petrographic study. And then we can also do a sprinkle mount for very different types of material. As you can see, that we have two machines, both in MLA and QuantScan. And this is actually running some samples right now. Here you can see in the monitor the actual place where the samples being analyzed. It's in a vacuum, and the samples being analyzed as we speak. There are various methods that this can be used for, like I said, for production, for exploration, for metal analysis, for anything that you want to determine mineralogy or determine mineral content of it. The detection limit for this machines are better than 0.1% versus an XRD, which more is a traditional trace geochemistry or mineralogy, where you're talking with detection limits but 1% to 3%. We also have XRD, as you can see. We have two XRD that we are able to analyze as well, to identify the crystalline mineral phases of samples, and which could be used by itself or can be used in conjunction with the MLA as a quality check. Is one of the key items for any of this is the sample preparation of these samples to ensure that your sample being analyzed is representative of your sample and what you're trying to determine. So here's our sample preparation location. We actually is very important to, like I indicated to you before, to properly prepare the sample. One of the best way of doing sample preparation is to stage pulverize a desired particle size, and that way you ensure not to over pulverize and to lose mineral texture on the samples. And then you would run different polishing procedures to mount that sample. You can, by this method, like I said, it is hopefully will help you with your processing or your exploration, and you can use, you can actually correlate the mineralogy, what is obtained from here, to your geochemical analysis. All right, you can visit our website, www.aclabs.com, and go under geometallurgy, and you'll find additional information in all the packages that we offer. Okay, thank you.
Hello, everybody. My name is Tassos Grammatikopoulos. I'm working for SGS in Lakeville, Ontario. I'd like to take this opportunity today to explain a little bit of the automated mineralogy tools that we've been using in Lakeville and in SGS in general to help our clients in exploration of mineral processing. For quantitative mineralogy, we're using QuemScan and TIMA-X that we just acquired recently. I'll focus a little bit more on the QuemScan that we've been using for the last 20 years or so. So really the QuemScan is an automated SCM. The principle behind that is similar to all other SCMs. That is, an electron beam interacts with a mineral, excites X-rays, and those X-rays are characteristic of the particular mineral. So if we're dealing with pyrite, then we'll see the peaks of iron and sulfur. And if we're dealing with chalcopyrite, then we'll see peaks of copper, iron, and sulfur. So the ratios, we use the ratios of these elements to define the different minerals. So what is the output of the QuemScan? There is a number of things, but it's not so much what we can generate using QuemScan analysis, but as a lot of labs can do that, but it's mostly, our focus is mostly the use of the data, the utilization of the data, and interpretation of the data. Essentially, one with the QuemScan can get anything from model mineralogy, mineral mass, to grain size, distribution, grades and recoveries, liberation and association of the minerals, and so on. So what does the QuemScan do? The QuemScan collects the X-rays, measures the particles, and then we create these pseudo color images that we use to calculate the liberation, the association of the minerals, and we evaluate the textural sort of characteristics of the ores. This is just to show you an example of the use of automated mineralogy in exploration. So the left graph shows the distribution of pyrite in red and chalcopyrite across a number of drill holes, assay reject samples, and the graph to the right shows the changes in textures and model mineralogy. So one can model these sort of parameters to map a particular deposit, either for alteration purposes, or if one is looking to track the distribution of the sulfides because they carry gold and so on. So very quickly, I always like these photographs because they're maps of the drill cores on a mesoscopic scale, and they tell you a story. Those photographs, those images rather, are from the Nechalacho Avalanche deposit in Northwest Territory. And what we do here is we map a polysection of about 30 millimeters in diameter, and we can identify the different types of minerals and evaluate their distribution. Just a little bit of a different or a simplified view. The left graph shows, or the left image rather, shows the distribution of zircon in the gangue minerals and a little bit of allanite or rare earths rather that you don't see. It can include allanite, monazite, bastnasite, and so on. And the image to the right shows a completely different distribution with less zircon, but with a lot more of the rare earths. So we've been using these sort of images and mineralogical maps to evaluate the variability of the textures, the ores, across the deposit, along drill holes, and so on. The same images can be used for different purposes. So one has to play with a lot of this data and parameters, but essentially we use different factors such as the PSSA. I don't have much time to explain that over here now. There's papers out there, that explain, the different functionalities and different parameters that we're using for QuemScan. But essentially, it shows you that a low PSSA shows quite a bit of coarse material, low and high PSSA, very fine grained material. Of course, things are not very simple as they always look. One has to play around a little bit with the data and make some proper interpretations. I'm going to show you a few slides from a project that we recently did for for heavy mineral sands project in southeast U.S. We examined a number of samples from Georgia, South Carolina, North Carolina. That's why you see GA for Georgia, SC for South Carolina, and NC for North Carolina. So we analyzed the samples as received, and so we calculated the most important heavy minerals. In this case, there was a little bit of monazite, rare siliciite, bastnasite, a little bit of zircon, and then some iron oxides, iron titanium oxides, and apatite. One of the functionalities of the quantum scanner is that you can extract really some powerful measurements. For example, in this case, I wanted to see the difference in the grain size between the different minerals and different samples. So I'm just showing an example of cumulative grain size distribution of one of the samples. I was particularly interested in the zircon and monazite, of course, but for our purposes here, you can see the blue line shows the monazite and the sort of dark red, the zircon. So you can see that the zircon is coarser and so than the monazite. And so the idea here is to evaluate the grain size of the minerals because it's critical for processing purposes. So one of the I mentioned earlier, one of the parameters that we extract from the quantum scan is the liberation of the mineral. So sometimes we have the analysis on a size-by-size fraction, sometimes on as a sieve sample, maybe at a pH of 200 microns or 300 microns, and we can calculate the liberation, the association of the mineral. So you can see that the liberation of the zircon varies across the different samples. So imagine that you have quite a bit of variability in some of the sands or any other deposit. You can predict what might happen when you start processing this type of material from the areas. So those are just particle maps that allow us to look at visually a little bit better the association of the zircon. And so this little group here is just free zircon. You can see zircon attached to or locked in apatite, but also zircon attached or locked in quartz. And of course, unless you grind these grains, these zircon particles will not liberate, which is also very critical because we can calculate exactly how much of that zircon population won't liberate at this particular grain size, let's say 200 microns. So what we did in this case, we upgraded the samples using heavy media, heavy liquids. And so you can see that the upgrading factor is very good for a lot of these minerals, especially ilmenite. Not so much for the monazite. It's very erratic because the mass of the mineral is not that high. But nevertheless, it gives you an idea of the upgrading factor for the heavy minerals. And so then I rerun some of the samples, the heavy fractions, through the quantum scan to see what is it that I'm getting at. And so I can see that monazite is quite a lot higher than the trace minerals that I found earlier, in the other sieve samples. Zircon is giving me quite a bit of population, and of course ilmenite and rutile. So these mineral sands are not, they have other minerals there, but those are the most economic sort of products. We use the data for different purposes. One of the things that we looked at was the roundness or the shape of the different minerals. So this is the shape of the monazite. So we can classify these particles based on their roundness and angularity and try to evaluate whether they're coming from long distance or short distances. And so we can trace possibly their provenance. We can go back to the source. But for metallurgical projects, when things are really tough and one has multiple rare earth minerals, we don't know which mineral we recover and which mineral we lose in the tailings. We can calculate recovery curves based on the rare earth grades or we can tackle a particular mineral. So instead of having rare earth grades, we could have monazite, for example, grades and recoveries. And so this is a little bit of a complex graph. It's not easy to explain over a minute, but it shows the grades and recoveries of from the QuantScan calculations and the actual metallurgical test work. So there are some differences, and we know why we have the differences for each particular case. Slimes involved and so on. Another powerful method, rather, is the chemistry of the minerals, especially when we're dealing with multiple minerals and we're looking for trace elements such as thorium, uranium, and so on. So we tackle this sort of work by doing electron microprobe analysis of monazite or allanite, so we can calculate the distribution of the different elements. Thorium and uranium and some of these deleterious sort of elements are very critical because they will affect the downstream process, not so much the mineral processing, the flotation or the gravity, but the hydromet side and how the hydromet people will approach the cracking of these minerals to extract the rare earths and sort of decouple them from thorium and uranium. So again, for exploration purposes, we can use the monazite chemistry to see if there where they plot, if there are any differences. We can enhance some of this population. But for exploration purposes and for the work that we did for this particular project, the Mineral Sands, it's critical because it allows us to compare the different populations of monazite. And so the ultimate weapon, in this case, is when we have is to calculate the earth distribution. So when one has the mineral mass and we have the chemistry of each one of these rare earth minerals, or even other minerals in other cases, could be, for example, arsenic in between a cyanopyrite and tetrahedrite, tennantite, and other minerals, and so on. But the application is the same. You know the mineral mass, you know the chemistry. You can calculate the distribution of any element. I show here rare earths because they're particularly difficult to tackle, and sometimes we think that we know what the case is, and we don't. For example, we know that zircon in this case contains quite a bit of rare earths, and you cannot reject it. This zircon is valuable, so it cannot really go into the tailings. So I wanted to sort of just wrap up here. I know I don't have much time, with in this presentation, but this is just a highlight of what we do and what we can, how we can apply our data. One thing that I really like to mention is that today with automated mineralogy, we can tackle a number of things. So the variability of the samples, the liberation of certain minerals, and apply it to exploration, geology, and mineral processing. One thing that we forget sometimes is that we don't really process or look at elements and metals all the time, but we're dealing with minerals. So it's so critical to understand the mineralogy because mineralogy essentially dictates the mineral processing, the ability of the mineral processors to recover these minerals and make a product out of it. So we can have high grades, high tonnage, and beautiful ores on paper and geochemistry, but unless we can prove as a first phase using mineralogy that this ore is economic and we can extract these metals, the ore has no value as long as it stays in the ground. So I'll leave you with that. Thanks very much for your attention, and maybe we'll speak very soon in the near future. Bye, everybody.
I will be showing two examples, two extreme examples of techniques that can be used during drilling programs. So let's go to the video.
We're going to show the way they do a pre-taping of the core in order to conserve the integrity of the core while cutting it, which is very unusual. So as you can see, they reconstruct the core first, as good as possible, and they do the taping of the whole core. And the line of cutting of the core is marked before, of course. And then we will see the detail how they try to configure the core, putting it together. That's where they do the sampling. Sampling after cutting it here. This is, by the way, Intrepid Mine facilities in Calingasta, province of San Juan, Argentina, where they keep the core. You can see they take good care of taking absolutely everything from the box. This is a low sulfide type of deposit, silver with some gold values. I'm going to show now the actual cutting.
a video of the new system that they just implanted here to collect the samples from below the water table. They're using this tub to collect the material. And then we are adding a flocculant. We'll show it to you later. Taking the sample. It takes about 2 or 3 tubs per sample, but we get the whole material. They are preparing the This is the flocculant. Se subí! Hey! Se subí! C'est le flocculant. J'ai placé beaucoup. C'est un peu...
Pas mis beaucoup, j'ai resté.
Ok, moins que ça. C'est déjà prêt. Regarde.
Non, de mettre moins que. Ils vont amener un autre ajouté encore.
Oui, mais n'a pas besoin d'ajouter plus que ça. Ça c'est bon. Ça c'est bon. So now we can do the decantation without a problem because the material rests in the back. Now they're adding a new tub with more material.
Voilà, 85, 86.
Allez, regarde. Oui.
On est là-dessus.
On décante. Use the material. So we are collecting all the material from the meter. And because of the flocculant, the water immediately gets clean and the sediments go to the bottom of the tub. You can see the bubble of air coming out. That is the last tub from this meter. Before they were trying to use the bags, the wrist bag, but they were losing probably 8/10 of every sample. Now we do the final decantation, and as you can see, the material remains at the bottom of the tub. So we can decant almost all the water. The next step is to mix it. Mix it well. And then we do the normal quarting. So they get the material from opposite corners. Usually 4 handsful make the 2 kilograms that they need.
is the sample. This is the split. The split, no, the region. So that was sample 95, 96. So probably we are using about 10-15 grams of 20 grams of the flocculant per sample. I just bought a bag of 50 kilograms, so they should have enough for it. So that's it.
Ah oui, le coude, il faudra faire il appareil.
This is the team that is preparing the blanks to be used at the RC and RAP. This is the result.